take it away.
Thank you. Introductions, and I'm very happy to talk in this virtual symplectic geometry seminars. Yeah. So I want to talk something about SYZ and KAM. And so KAM is named after these three famous people in symplectic geometry. K is Kolmogorov, A and Arnold, and M is Moser. And KAM is a famous theory that describes dynamical systems, which is close to integrable systems. But I want to use some particular version of this KAM theorem, which I want to explain. So I consider this symplectic manifold, and KAM is a local theory, so it's just anything about compactness. And suppose that this symplectic manifold is a fiber bundle over B0, and the fiber is a Lagrangian torus. So we consider this Lagrangian torus fibrations. And suppose we have this F0 symplectic diffeomorphism, which is of this particular form. So let me remind you that this is a Lagrangian fibrations. So the base space has a natural affine coordinate that's called action coordinate. And there is some angle coordinate of the fibers. That means that if you take this Hamiltonian vector field of this ice action coordinate, and that is this ddpi, right? And the fiber is this Rn divided by Zn. And this symplectic diffeomorphism is supposed to preserve this. So we require that F0 pi is pi. And also on each fibers, we require that this is a translation by some number, some element fq, depending only on q. So this is a some kind of integrable systems. And I assume that this differential of this f that goes from tangent space of B to this tangent space of fibers that are Rn. And I assume that this is an isomorphism. I think this is known to be a non-degeneracy conditions in KAM theory. And we consider one parameter family of deformations of this symplectic diffeomorphism. So all F epsilon is the symplectic diffeomorphism. So now this famous theorem, which is a version of KAM theorem, is the following. In this situation, you have this F epsilon. Then you have this subset B epsilon of the base space, and for in each element of this B epsilon, you have LB, that is a Lagrangian torus. And this Lagrangian torus is Hamiltonian isotropic and very close to this fiber at B. And the important condition is that this one is invariant by this F epsilon. And the volume of this of the set is almost full volume. So this is the famous KAM theorem. And I don't want to prove it, but this is a very classical and important result. And such a tori is called a KAM tori. So this is one classics in symplectic geometry. And I want to go to the next things. Another three famous people, Strominger-Yau and Zaslow. And this SYZ is famous in this mirror symmetry kind of result. And this Strominger-Yau-Zaslow proposed to construct mirror of Calabi-Yau manifold by somehow compactifying dual torus vibrations. And I want to mention some particular situations that this SYZ vibrations are expected to appear. That's called the maximal degeneration point. So we consider this one parameter, we consider a family of scalar manifold parameterized by two-dimensional disk. So pi is a holomorphic map. And we consider this MQ, that is a fiber. We have this D2 and this point. We have a fiber. And we assume that this fiber are smooth scalar manifold or non-zero Q, and maybe Calabi-Yau. And the fiber at zero, so we consider this zero, the fiber at 0 is singular, and it is a normal crossing divisor. And some condition we assume is that M0 is a union of several irreducible component di, and they intersect in a maximal sense. I mean, this total space is so this is complex dimensions. So total space has n+1 complex dimensions, and di is codimension 1, complex codimension 1. So if it intersects transversally, so n+1 is a maximal number, and we assume that there is a point that this actually n+1 irreducible component intersect. So that is called a maximally degeneration point. And it is kind of now believed, and that is, as it first proposed by Strominger-Yau-Zaslow, is that in these situations, there is some map from this regular fiber MQ to some manifold B and some subset B0 of B, so that if we restrict this projections to this to the inverse image of B0, then this is a Lagrangian torus vibrations, and the complement of this B0 in B has codimension 2. That I think is now expected by many people, and this is called SYZ fibrations, and this singular and the regular fiber is called SYZ torus. I'm not so much sure how much in general this kind of thing is constructed, but there are a lot of examples, and it is believed that this exists in general. So in this particular situation of this maximal degeneration point, I want to study some particular symplectic diffeomorphism. That is the following things. So first, I want to put some Kähler form on this. So we have a structure in our situation. We have this space and the projection to disk, and on the total space, on this total space, I want to put some symplectic form, and there are possibly two choices. One is just to reconsider some Kähler form on this total space, and the other case is that we put so-called log Kähler form. So in a very simple case, that this total space is just complex numbers, and this is 0. Then the usual Kähler form is just like this, right? This is polar coordinate RdR plus wedge d theta. And long Kähler form is something like which blow up infinity, and this divides at 0. So there are two choices, and the story is likely to change, but I want to explain both cases. And we take some particular Hamiltonians. That is just the absolute value of this. No, this is not true. This is pi. Sorry. So I mean, so pi is a map. Pi is this map, right? From X to this disks, and we just take its absolute value. So this is some real value functions on the total space, and we use this symplectic form, and then we define Hamiltonian vector field associated to this Hamiltonians. And this map CHT is a one parameter subgroup of group of transformations of this particular symplectic diffeomorphism. And I want to take this Poincare first return map FQ. So that's the following things, right? I mean, we consider this disk D2, and then we start from Q, and so this absolute value of Q is epsilon, and this is a radius epsilon S1, and of course this is a Hamiltonian vector field, so it preserves Hamiltonians. So it goes on this circle, and of course H is somehow it is radius, so it goes this way. So Hamiltonian vector field always go this way, and on the above we have this MQ, and then we come back, and this is the first time when this map when this one parameter group coming back. So this is a usual construction of Poincare map, and one can easily show that this FQ is a diffeomorphism, and is also symplectic diffeomorphism. So we have some particular symplectic diffeomorphism on MQ. So I want to explain one baby theorem. If you consider this FQ, which is a symplectic diffeomorphism from the fiber, from generic fiber to generic fibers, and we consider this SYZ vibrations, and the claim is that we have this subset BQ on B0, which has positive volume, And for each point B on this BQ, we have some Lagrangian submanifold in a on MQ, which is preserved by this symplectic diffeomorphism and is closed and Hamiltonian equivalent to the SYZ fibers. So this looks like very much like a KAM theorems, and this looks pretty, but only bad point of this theorem is it's a bit too easy to prove. So I want to mention that this is the main theorem, but I mean, to be a main theorem, it is a bit too easy. So I want to prove something more, but I want to do something more, but this is just the beginning. So why it is so easy to prove it? So this is so easy, I want to explain the proof. But at the same time, I want to introduce some particular situations I want to study more. So let me consider these particular situations. We consider this quartic surface in P3. It is just these equations, right? G0, G1, G2, G3 is Q times G0 force, G1 force, G2 force, G3 force. So you look this, you have this, so there is some famous Lefschetz pencils for this quartic. It is defined in the following way. So we consider the map pi from some blow up of P3 to P1. It is just this map. So you can just take the ratio between left-hand side and right-hand side, right? So this is a complex number. And this is defined on this P3, but of course, on the basic locus, it means that if both the denominator and the numerator became 0, you need to do something to have a well-defined map. But there is a very well-known process. We just blow up this basic locus several times. Then we get this map pi from this blow up of P3 to P1. And that is a very typical example. So this is more global, but this is a typical example of one parameter family of deformations. And this kind of family is studied much in this kind of family is studied much in mirror symmetry. And the Hamiltonian is just the absolute value of this. So we consider this first return map of this particular Hamiltonians. Then I want to consider this point 1, 0, 0, 0 in P3. So that is of course that is a fiber of 0. So we consider this right. We consider this Hamiltonian vector field in the neighborhood of here. So I use this homogeneous coordinate. So inhomogeneous coordinate. Right. Then this Hamiltonian, you see that this is you divide it, but then this is a small number. So this is very close to this G1, G2, G3 product absolute value. You have a higher order term. Then we just take this approximate Hamiltonians like this. And then our symplectic form is very close to this standard form. You have some small difference, but so that this is W0. So the Hamiltonian vector field and dynamical system you study is very much a kind of trivial one. You have just the H0, which is the product of the three thing and this absolute value. And the symplectic form is just the standard ones. And then this is obviously an integrable systems. So you have this absolute value of Zi. That is a, then this absolute value of Zi Poisson commute with this H0 with respect to this trivial simplex structures. So you have three first integrals, and then this is integrable systems. And then you can just apply KAM theorem itself to show that there is a positive, there is a family of, you consider this map, right? You have a map from this MQ to this B, right? Suppose you use this to get this SYZ fibrations, and you have some positive. You have this BQ of positive area in this part, in this small part, so that you have a KAM tori. So you can just apply KAM theorem to get this this baby theorems. You see that this argument can be generalized in a complete generality, but as you see that this is very much easy exercise of the application of KAM theorems. So this is a kind of a beginning of the stories. But so since this is too much easy, so I want to mention one theorem which I want to explain maybe later on is the following things. In this particular example of this pencil of quartic surface, this symplectic diffeomorphism has 408 fixed points. And this seems to be optimal. And if you look this Betti number, MQ is a K3 surface. So its Betti number is 24. So it is likely that 24 is very easy to get, but we have a much more fixed point in this particular example, like 408. Okay. So, but before explaining this kind of things, I want to explain how this homological mirror symmetry is related to this story. So let me recall this relation to this homological mirror symmetry and SYZ fibration. So first I want to recall how this SYZ proposed in this kind of situations. So in this case, I want to put, are there any questions or something? Oh, no, it's okay. Yeah, so now we consider this kind of regular part of SYZ fibrations, and they consider this dual torus fibrations. So you take fiber-wise dual, you have another fibrations, and the symplectic structure of M0Q gives a complex structure of this dual torus fibrations. And what is conjectured by SYZ, and maybe kind of more and more making progress, is that if you use this holomorphic disk count of this side, maybe MQ, right? Which bounds this SYZ tori, and then it gives some deformations of these complex structures so that it extends to the complex structure of these compactifications. And you get this complex manifold, and this is expected to be this is called SYZ mirror to MQ, right? So this is a way that nowadays people understand how this SYZ mirror constructions works. And so I want to use this kind of pictures. So now we consider this SYZ fibrations from MQ to B. And it is known that in many cases, this SYZ fibrations came with the Lagrangian sections. S0. It's a section from B to MQ, so that the image is Lagrangian submanifold. So now we consider this in each point to B0. So B0 is a base part. All fiber are honest regular tori. And we consider this fiber of SYZ fibrations, SYZ fibers. And this has a kind of, this TB is somehow identified with Rn divided by its lattice by using this angle coordinate. And we fix this point, and we take this point as a unit. So this is something like a canonical isomorphism, but up to translations. So we use this S0 to fix the base point. Then this fiber has canonical structure of abelian group. And then we consider this point B, which is in a kind of singular locus. And then we consider this regular part of the of this fiber. So this TB is in general very much singular. Then the first conjecture is that you have a sequence BI on a regular point, so that this BI converges to this B. Then we consider this sequence of structure of abelian group TBI. Then it is expected that this converges to some structure of abelian group of TB length. So I mean something like this. So you have this singular fiber length, and you have 2 points. Then you take some transversals. Then you end up with this another point. So this is a TBI. Then you have this XI, YI, right? And then you take this sum, XI plus YI. Then this conjecture somehow expects that in this limit, you have some limit. That should be this sum. So in this way, you may expect that you have some structure of abelian group on this regular part of the fiber. And probably this is not so difficult to prove in many examples. I mean, something we need to prove is that if you consider kind of, you have this kind of B, and here consider the monodromy around this small loop. And if this monodromy is in a sense a group homomorphism, then you have a limit. that's the kind of things we can expect. But this I wrote it conjecture mainly because there is no good definition of SYZ fibration. So but anyway, this is a conjecture. So now then we expect the second thing is that there exists another Lagrangian section S1. So that if you consider this limit of FQ, that then it preserves this SYZ fibrations, and on each fiber, this F0 is just a translation of this SYB. So this is related to this assumption of KAM theory. And this limit we take the following way. So you have this Q0, then you have this Q, then we go this way. For example, if this is X is this coordinate, then we take this Hamiltonian of X to go from this one to this one. And then you take this first return map of this FQ and come back. So this is the family of maps from MQ0 to MQ0 for fixed Q0. Then you can go to the limit. And then we have this kind of behavior is expected. So now let me, so I want to explain this, how this is related to homological mirror symmetry. So we consider this mirror complex manifold. Then first of all, we have this first section S0, and the conjecture is that this image, that is a Lagrangian submanifold of the total space, is a trivial line bundle. It's a structure sheaf. Actually, this is the reason why we expect that this S0 exists. You have some structure sheaf that mirror in some sections. And the next thing which is expected is that mirror of this monodromy. So you consider this FQ, that is a map. FQ is a map to MQ to MQ. Then it induces this automorphism of the category of this Lagrangian submanifold. Then if you believe this homological mirror symmetry conjecture, it should give some automorphism of the derived category of coherent sheaves. And it is expected, what is this automorphism is? It is just a tensor product of some particular ample line bundle. For example, in an example of this quartic surface, I think this P is, I think, all of 4. So you have some particular line bundle, then you can just take a tensor product and you get this mirror to this one. Then, so then if you believe this, then skyscraper sheaf is just a sheaf which just is a supporting a point. Then this operation, taking tensor product of line bundle, of course preserves skyscraper sheaf, right? Line bundle on a point is just a trivial. So this is some reasoning that this Lagrangian fiber is preserved by this symplectic diffeomorphism, because the mirror to the Lagrangian fiber is expected to be skyscraper sheaf. But this is a bit superficial, and there are some cheating, because this implication probably, this just implies that F0 TB is Hamiltonian isotopic to TB, because this is just the automorphism of the category. And if you want to study dynamical systems, this is not so strong enough. But I have some very strange, maybe it's a bit strange idea that if you prove this homological mirror symmetry over Novikov ring, not Novikov field, probably this equality holds. So the idea is the following things. You consider Frey homology of F0 TB and TB prime over Novikov ring. So for B is not equal to B prime. And if this is 0 for all B prime, then this implies F0 TB is equal to TB. Why? So you have this TB, right? Then if this became something like this, then you consider this nearby fibers. Then you see there are, oops. So there are many intersection points. And of course, if you take this Novikov Frey homology with Novikov field, this vanish. But over Novikov ring, you have some kind of a torsion element. So this is the kind of reasoning, and this vanishing probably holds if you can prove this homological mirror symmetry over lambda 0, because this process seems to be okay. But I think practically there is no case that homological mirror symmetry is proved over lambda 0. Over lambda, nowadays many examples, but lambda 0 is much harder. But anyway, this is just a kind of speculations. Okay, so now I want to explain a bit another things. So we consider this three Lagrangian submanifold MQ, and suppose that L1, L2, L3, and EI is a mirror to Li. So this is a mirror to Li. And then if you consider this tensor product, suppose E3 is the tensor product of E1, E2, then it is expected that this tensor product operation is related to this relation. It means that if you take this point x1 in L1, y in L2, which project to the same place, so you have this B, and you take fibers, and you take this like this, and you take some. You know, fiber has a structure Barbian group. So this is L3, and it is expected that this is equivalent to this. I don't know how much it is proved and who first proposed it, but at least I heard it from some talk by Konsevich a couple of years ago. And there's a reason that's why it is, but I don't want to explain so much in detail. Then, if you assume this, then you know this is a kind of mirror to F0 tensor product, and you look these relations. This implies that this F0 is just sum over S1 P. P is a mirror to S1. So this is the reasoning that how this assumption is related to homological mirror symmetry. And there are another thing that you consider this derivative of S1, and have this non-degeneracy condition of this KAM theory. And then you look this some calculations in semi-flat mirror calculations. This derivative is known to be the curvature of this line boundary P. And we know that this P line boundary is an ample line boundary. It means that the curvature is positive, so this is invertible. So this non-degeneracy condition of KAM theory is satisfied. So that is the reasoning why this is supposed to be. But they all are just conjecture. And I want to show you a few examples. So in a case when this symplectic manifold is 2 dimensions, it's a K3 surface, you have this SYZ fibration. But in this case, SYZ fibration is so-called hyperkähler twist of elliptic fibrations. You have many elliptic K3, and you take hyperkähler twist, then you have a Lagrangian tori. And then this singular fiber is actually, in this kind of case, is classified by Kodaira and Neron. And the fact that this, this is the conjecture that this singular fiber also regular part. So this what I say that this guy has a group structure. And this is basically kind of important part of this Neron's theory of Neron model. So let me show you some few examples of how it works. So there are, I just take 2 examples. Let me take this AN singular fiber. You have this N S2 and NS2 which are intersect in this particular ways. And this is the N is the collider classification tables. So we take regular part. It means that you remove all these intersection points. So you have this N copy of C star, C minus 0. And this has obvious group structure. This is the group and this is group. And another example is this D4 singular fiber. So D4 singular fiber, you have this 1 S2, which has multiplicity 2, and you have a 4 S1, which has multiplicity 1. And then you take this regular part. So the regular part, this S2 has a multiplicity, so you used to throw it away. And then you have this 4 copy of complex numbers, plus but then, if you just look this table, Neron's table of this, then this is a group structure. So you have this kind of things. And you look this group structures, you know how this dynamics, how this F0. So F0 should define some maps, but it should look like this. So this is somehow, kind of natural map on the sisters, and this is some kind of flows on this thing. And my question is that are there any, we can generalize it to higher dimensions to kind of Lagrangian version of neuron model. For example, you consider this three-dimensional cases, then what is the singular fibers and how is the abelian structure of abelian group and how you can classify. But that's I don't have any idea yet. Okay, so now I want to go back to this examples, and especially I want to explain this calculation in the case of K3 surface. But before, I want to do some warm-up examples, so cubic curve. So before going to this K3 surface, I want to discuss this cubic curve. So the cubic curve is just this. G0, G1, G2 is Q times G0 cube plus G1 cube plus G2 cube. And you have this function G0, G1, G2 divided by G0 cube plus G1 cube plus G2 cube. And this is defined or certain blow up of P2, maybe 9-point blow up. And then you take this H as an absolute value of this particular rational functions. And the FQ, the map between this cubic curve, is a first return map of this Hamiltonian vector field. And I forgot to say, so in these calculations, I want to use scalar form on this total space. And in a homological mirror symmetry pictures, I think it is more natural to use long scalar form. And I want to mention the relation of this scalar form on X and long scalar form later on, probably at the end of my talk. But anyway, for a moment, I want to use scalar form. Now I consider this P2. So this is a toric picture. Then on P2, you have this 3 domain, which is a neighborhood of the vertex. And I think I explained in the baby theorems that in this neighborhood, this dynamic is something like just very simple. Right? So you can just directly apply KAM theorem so that, I mean, if there is no, if just this guy and this guy, then everything is integrable systems. And you have a small perturbations, you can use KAM theorem itself so that almost everywhere you have invariant torus. So there is not so many things to talk. But there is another part. So on this near the vertex, you have some another domains. And I want to explain how this maps looks like here. So here, so I want to use this inhomogeneous coordinate. Z is Z1 divided by Z0. W is Z2 divided by G0. Then Hamiltonian is just these functions. ZW absolute value 1 plus Z cube plus W cube absolute value. And I want to make some approximation. So this kind of thing is very popular in Hamiltonian dynamics in this sense. So, so this guy has this plus Z cube. But I want to eliminate this term to simplify the Hamiltonians. Why I can do it? So in this domain, one observes that this W divided by 1 plus W cube is away from 0 uniformly. I mean, this one go to 0 here and here, right? W is 0, W is infinity, then this one goes to 0. So you cannot forget this Z cube. But as far as this is away from 0, and Z is this, and the absolute value of Z is something like epsilon. Epsilon is absolute value of Q. So this term is very small. So I throw it away. Then I want to study this H prime and its Hamiltonian vector field. And what's nice about this is that then you have a separation of variables. Z and W is decoupled. So the Hamiltonian vector field is something which came from this part is just the dd theta, it's kind of rotations. And this part is some particular Hamiltonians. And this is slow because this is epsilon. And so we have this decoupling. And this F, so Hamiltonian is this form. And this is slightly different from this, but something we need to think about is this Fujii study metric. So we take this omega on P2, that is the Kähler form of Fujii study form. And if you take this R, I mean, R is the Z is R plus e to the power 2 pi I theta. So if this is length, it's something like a 1 over 1 plus W square in a Fibonacci metric. So I want to take something like a normal derivative of H prime, not this R derivative. So that's why we have this term. So what we have is this. So you have this Hamiltonian vector field which approximates the one we want to study. That is the sum of this dd theta, and that is the sum of this dd theta and epsilon xx. So we have this z plane, and in the normal direction is you have this very fast dd thetas. So it means that if you want to see this first return map of this Hamiltonian vector field, it is basically the time epsilon map of this vector field, right? Because this is just, so you have something like here, and you have something here, then you see what happens when you come back. So this first flow is just this rotations, and when you come back, you move a bit on this Hamiltonian vector field of this small f. So this is a kind of usual process on this perturbation theory. So the first return map FQ on this particular part looks like this epsilon map of this Hamiltonian vector field. And what's nice is that now we have this projective space and some particular Hamiltonians, and you can integrate, right? So you can just look this level set of f, and that is this. You just draw this level set of this particular functions. That's easy, one complex variables. You have this picture, and these 3 points are critical points, and you have this 3 points, and this point is something like 1 plus w cube is 0. So actually, you know, you need to blow up this basic locus, and this 3 point is exactly you need to blow up. So the dynamics is something like this. So I mean, here you have this kind of very closed orbit, and then you have this hyperbolic, and you have this elliptic fixed point. So that is this x epsilon. So we now understand what happens here, and maybe it's better to say that this is actually an approximate picture, because I thrown out this d cube. So actual picture is probably more interesting. For example, if you look this part, then you have this these things, right? But this is an approximation. So the kind of general picture should be something like this, right? I mean, this stable manifold and this unstable manifold, in this approximation coincides, but in general it should intersect. And this is a famous picture which goes back to Poincaré, right, 100 years ago. He found that in this kind of situations there is a chaotic dynamics. So this should be actually the case, but anyway, we understand how this, and you can see that we can still apply KAM theory, because most of the spaces is just integrable. So at least we can show that in this example you have this 6 fixed point on each of the edges. So in total you have this 18 fixed points. Okay, so now this is a warm up for the quartic surface, for this cubic curve, and I want to continue to understand what happened in the case of this K3 or quartic surface. So this quartic surface, so as I explained before, we have this map pi from blow up of P3 to P1. That is a ratio. So this one divided by this, and the Hamiltonians I want to study is absolute value of this ratio, and the first return map of this Hamiltonian is something I want to understand. Okay, so now this is P3, and we have various parts we want to understand. But first of all, this purple part, that's a neighborhood of this vertex. Again, this is something like I discussed in the case of this baby theorems. So this part, everything is simple. It is just very simple dynamics of this G0, G1, G2, G3, and you can just apply KAM theory directly. So that's not so much things I need to explain. And so there are another part which is the neighborhood of these edges. That part may be a bit slightly different, but this part actually is rather similar to the case of cubic curve. You can do this approximation in a similar way, and you can analyze it. Maybe I will go back this at the end of my talk, but maybe I just want to mention that this is very similar to cubic curve cases. And the main thing I want to explain on this example of this pencil of quartic curve is what happens on this surface. So you have this two-dimensional part of the faces, and I want to understand this how this first return map behave in the neighborhood of this particular places. So I want to do the same process. So your H, in this case, is something like a ZW B, sorry. ZWB absolute value and 1 plus Z force W force plus B force, right? This is the actual Hamiltonians. But again, on this domain, I want to drop this B. So this form. So B is a direction which is normal to this plane. So what's good is again, you know, the B part, and this other part is decoupled. So kind of Hamiltonian vector field of this H prime is something like a dd theta plus epsilon of xf, and you know this B is r e to pi I theta. So this theta direction is a fast direction, and this is a slow directions. So that's very popular ideas used in this perturbation theory. So if you want to see the first return map of this approximated Hamiltonian vector field, then you need to know is that this F time epsilon map of this Hamiltonian vector field of this particular Hamiltonian F. And F is this functions. And this is close to C, and you have another thing here. This guy is also kind of, you know, this Fubini study form. Without say it is a kind of, you know, if you take this R, then it is a length of this R on this point. So you have this one particular Hamiltonians, and the vector field I want to study is a Hamiltonian vector field of this F on this on P2 with respect to Fubini study form. And yeah, actually a few weeks ago, I tried to calculate this Hamiltonian vector field, and it is not so very easy. And something I finally found is that if you try, at least I can calculate the critical point of this vector field. So this vector field is going to infinity at this point. That is a kind of, you know, basic locus, and this zero here that I want to remove. Then on the outside of here, I want to find a critical point, and there are exactly 16 critical point. That is a point when this Z and W are fourth root of unity. And this is a lemma. And this lemma is actually very elementary to prove, but it's not so completely trivial. So it takes me for 5 days to prove it, but it is very elementary. So I don't want to explain its proof, but you have this 14 critical points. And those 14 critical points, of course, will be a fixed point of our FQ. And this is the approximate picture, but this 16 critical points are transversal, so it remains to be an actual fixed point. So if you see this F, and of course you have a Hamiltonian vector field, you need to know what happens on the level set of this F. And this level set is some 3 manifold, which is rather complicated. And I think that this XF is rather chaotic, rather ergodic or chaotic on a general value. And when F is close to 0 and close to infinity, then you can again see KAM phenomenon that F is kind of close to integrable. But in the middle, probably you have very chaotic dynamics. Okay, so now this is how we understand F. And another thing we need to understand is what happens on this sigma 3. So let me remind you that our dynamics and our system is something like this, right? So our H is kind of B, W, Z divided by 1.B cube, W cube, and Z cube. So something which I need to think about is that when this denominator go to 0, then this h is infinity. So you need to understand its neighborhood. And of course, we blow up. But so we need to we understand what happens in this neighborhood. So that is this this curve, quartic curve. And you know that this is a quartic curve, so its genus is 3. And I want to understand its dynamics in this quartic curve. You can do similar perturbation business. But I want to take shortcut that this quartic curve has some symmetry. So the group of symmetry is this group of order 96. So this group is the following things. So for this Z and W, this goes to epsilon Z and epsilon prime W. I'm sorry. Epsilon prime W and epsilon force and epsilon prime force is 1. And obviously this guy and these functions are all symmetric with this. So this is the symmetry of our Hamiltonian of our symplectic diffeomorphism, and also this all curves. And this is this this part. And this S3, to see S3, you can just change this to a kind of homogeneous form, right? And then you have this set ABC, and this group of symmetric group just exchange this ABC that acts here. So this is this group. So this is 16, and this is 6, and you have 96 group. So you can take this group and divide this genus 3 curve, and you see what it is. It is just this S2 with 3 orbifold singularity. And these 3 points are exactly this order 8 and order 2 and order 3 singularity. You can check this by just calculating Euler number, but I don't do it. You can just do it. So then what happens? So if you look this symmetry and all this symplectic diffeomorphism is invariant by this symmetry, so it implies that all these points will actually be a fixed point. So you take this B, then you know, isotropic group of B is 2. So this became 48 because this group is 48 points on this genus 3 curve, and this genus C. Oops. There it is. Yeah, this C becomes 32 points, and this A is this, so this became 12 points, and I can say what is these 12 points, right? Because this is sigma 3, so you have this P2, right? On this in this P3, this 3P2, and this sigma 3 intersects this P2. So each so sigma 3 and each P2 intersect by 4 points, because this is degree 4, and so you have the 3 edges, and these 3 edges correspond to this 3 P2. So you have this 12 points here. That is exactly this point A. So we understand how this happens, and I believe that this dynamics on this thing is just this, but this is not yet completely proved. But you know, so what is this? You have this orbifold, and one can expect that there are some Hamiltonians on this surface, which is invariant. Then that one control this dynamics, and it should be here. And if you look this particular point, then so this is a B, so you have the order 2, then the dynamics near there looks like this. So this is a hyperbolic point, and this point is an elliptic point, and this point is an elliptic point. So that's this dynamics. So for example, then from this things we can say how many fixed points. So in each surface you have the 16 points, which is just a critical point of this lies interior. And 48 plus 32 lies on this genus 3 surface. It's 94. And you have another 4 on each edges, and you have this 408 points. So that is this. But this is a kind of one of the consequences of what I explained. But something nice is that this picture explains this how this FQ looks like rather in detail. of course, this chaotic level, we don't know what happens, but in many places, we have this something happens. And also in the neighborhood of this sigma 3, we have some kind of KAM theory. We have just a lot of invariant tori. And in the neighborhood, the normal direction of this is something like a disk. And this is this kind of zero, and you have this S1. So you have this S1 plus this normal direction gives this KAM tori, and you can apply KAM theory. So this is something we expect for this FQ. Okay, so now this is the description of FQ, and so you see that this description of FQ seems to be rather different. So you have this using this long Calabi-Yau, long Kela metric. Then you see that the picture is something like a kind of QP go to QP plus FQ, right? And you have some small perturbations, and the KAM theory says that only very small part is chaotic, but here it seems that there are big domains of chaotic, and I just want to speculate what happens, because I want to make this precise, but it's not yet. So the story is the following things. So I have two situations. One is just I use this long Kela form, and the other case is just I use some kind of Fubini-Studi or blow up of Fubini-Studi's form on this total space of the pencils. And these two are somehow related but different. So how they are related? So first, we consider this domain, which is a neighborhood of the vertex. And if you use this Fubini-Studi form, this domain is rather small, right? It's a positive area, but it's kind of, everything works only on this very small neighborhood of the vertex. But if you know what this long Kela form looks like, then this domain is a big part if you use the long Kela form. That I think is a usual picture, right? Kind of, one is R dr, blah, 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 and the other is R inverse dr, right? So kind of, R0 part is very small on this usual Kela form, but very big in a long Kela form. So this part is kind of occupied most of the areas. And that is this kind of, in a SYZ pictures, almost everywhere is regular fibers, and you have these translations, and that's survived by this small perturbations. Okay, now we consider this part, which I spent a lot of time to explain. So this part is actually very big in a usual Kela form, but if you look in a long Kela form, this part is actually very small, and it gets smaller and smaller. And I think in a limit, this just became a single tori. So you have this big domain in longer Kela form with just one T2. So what is this FQ mean? So epsilon is the absolute value of Q. Then FQ is so as I said that this FQ looks like time epsilon map of this some Hamiltonian vector field. So when epsilon goes to 0, of course, then this gets a constant map. And in the limit, this T2 on this T2, just a FQ is just a constant map. And that you can easily see in the case of cubic curve. In a cubic curve, you have this funny picture. And this funny picture just shrinks to just one S1, and the map is constant. And I think the same is true in this quartic case. So you have some particular T2 where this map is constant. So this naturally fits to this SYZ pictures. But then I wonder that for this rather complicated dynamics we observed on this on the surface, that is the following things. So what do we find the following things? So we take this FQ, and Q is epsilon. So let me take F epsilon, and epsilon is 1 over n. So this gets to constant, but if you want to see something non-trivial, then we repeat this F epsilon, iterate n times. So then this looks like a time 1 map of this XF. Then when epsilon goes to 0 or n goes to infinity, you have some non-trivial map, and also you need to expand this normal direction to this particular T2. Then you get some symplectic diffeomorphism, which is non-trivial, and the conjecture or speculation is that the particular symplectic diffeomorphism I just described using this Fibonacci form is exactly this limit. So that's something, you know, so if you recall what KAM theory is doing. So in KAM theory, you have this integrable systems, and you perturb this symplectic diffeomorphism a bit, then many tori, livable tori remain to be invariant tori just after perturbations. But there are some tori which are destroyed, and which tori are destroyed is known in KAM theory. It's destroyed by resonance. So I mean, it's kind of, you know, the classical theories, there are something called a small denominator. And small denominator in a physics language is related to this resonance. And this particular tori I just mentioned here is very much resonant, because this is a tori on which the map FQ is constant. So I mean, it's a strong sense is resonant, and you just small perturbations. This tori is likely to be destroyed. And the one thing which is not so much well understood is that after some livable tori is destroyed, then there are some chaotic domains, and what happens there? It's one kind of interesting problems. And something I believe is that if you just do this process to expand this resonant tori and you repeat your symplectic diffeomorphism, then you have some limit picture of how this dynamics is destroyed. And so this is some chaotic systems, and that I think is we observed here. So this is kind of, you know, very chaotic, but it has a lot of structures. You have this genus 3 surface in it, and you have this 90 something fixed points, and you have this level set. So this kind of rather interesting dynamics is something which appeared here. That's a bit speculative, and so now I want to explain the last thing. It's about on this what happens on this lines, and you can do that similar business in the case of cubic curve, and your dynamics is something like reduced to this picture. So this is very similar to this cubic curve picture, but you have this 4 elliptic fixed point because the degree is 4. So that is this, and also you have this normal directions, that is S1. So you have a 4-dimensional dynamics. So this is the 2-dimensional part, have another 2 dimensions. And on this red part, you have these pictures on the fiber directions. You have this one point, and if you look this blue point, then you have this kind of picture. You have this S1, which is on this rotations, and this direction is something like you go through. So that is this how this dynamics looks like. So you know this limit pictures on this using Fibonacci forms. And then I want to try to do the same similar thing to go to this long scalar form. Then what one think is that following thing. So this one has you have this directions, kind of horizontal directions, and you think about this what this long scalar form looks like. Then this direction is something which is kind of shrink. So in the limit, this got completely shrinks, and this funny picture just everything just lies on one line. So on one line you have this 4 red fixed point and 4 blue fixed point, and the fiber is something like this and like this. So you take the fiber, you have this picture. This red one is a kind of node, and this blue one is S1. So you have this thing, and this is exactly this A4 singular fiber. And I believe that this A4 singular fiber is this A4 singular fiber in SYZ pictures. Probably one can try to prove this, and you know, this kind of thing is related to how can we prove existence of SYZ fibrations in this kind of things. So I don't know how much it is known, but I believe this is a limit A4 singular fiber. But if you try to do the similar game as I explained in the last page, is the following thing. So you think that so you know at the beginning this A4 singular fiber is some kind of a dynamics is rotations in this blue lines. It's half rotations. But then if you turn on Q, so this A4 singular fiber is destroyed, and what you see is that this dynamics. So you have this. So what this dynamics means that you have this S1. So in this neighborhood, this S1 goes slowly to this one, right? That is this line. And this red point became some kind of elliptic fixed point in this 4-dimensional picture. And again, that this line is actually just approximate. So you have this kind of interesting Poincare type phenomenon. So that's something kind of what happens after this A4 singular fiber is destroyed. So this is not a theorem, but the conjecture is that if you have this SYZ fibration, you have some A4 singular fiber, which is fixed at time 0, but then after taking Q gone, you get this kind of phenomenon. Okay, so now that time is up, and this is something I want to explain. So this is just propaganda in the last page. So thank you very much. I stop here.
Great. Let's thank the speaker. Thanks very much. Before taking questions, I'd just like to post 2 links. The first one is feedback. The first one, sorry, is speaker suggestions. The second one is feedback for us about the seminar. And let's see, Kenji, you have several questions. The first one is from Denis Aru. Denis, go ahead.
Yeah.
Sorry, I didn't follow closely enough, but maybe it's my fault. But what is the expected expectation of the 408 fixed points? I mean, which line bundle on the mirror K3 is being matched with the monodromy here?
No, this 408 fixed point is about this monodromy at maximal degeneration point.
Sure, but that should be mirrored to the monodromy of the mirror family, and you say it should be corresponding to tensoring by some line bundle on the mirror core.
Yes, the line bundle is O4.
Oh, O of 4 has that many sections?
No. I think I don't understand why this O4 section of O4 is related to this fixed point. Is there a general result? You have this Symplectic diffeomorphism. And probably it is in the limit, it became O4, right?
I see. So you're saying the number of fixed points doesn't have to match with the cohomology of O of 4.
Yeah. I think, if you just use this kind of cohomology calculations, probably what one get is a Lefschetz fixed point formula. In this case, that fixed point formula gives you 24. And this 24 corresponds to the fixed point which lies on edges. And other than this 24, if in the limit picture, you have this 4 T2, which is completely fixed by this Symplectic diffeomorphism. I think the baby example is this cubic curve. You have this T2, right? Then its mirror is just a kind of tensor product of O3. And something what happens in this case is that you have this three orbit, which is completely fixed by this. So this F0 is a triple dent twist of the kind of three composition of dent twist, and you have 3 S1, which is completely fixed by this map. But then if you change this picture a bit, you have this funny picture, and on each part you have the 6 fixed points. In this case, you have 18, and I don't see how this 18 has some particular meaning on this kind of section of line bundle.
I see. Thank you. Yes, that's very convincing.
Let's see. Andrew, did you want to ask anything further on your question?
My question is the same question as Denise. He just finished typing before me, and I didn't read it. Yeah. So never mind. Yeah.
All
Thanks.
Right. Let's see. You have a question from Arnav. Arnav, go ahead.
Thank you for the talk. Could you say anything explicit about your FQ and F0, and especially S1 in the case of the Hitchin integrable system?
What? Could you explain? Could you tell me?
Could you say anything about your constructions, especially the S1 change of coordinate in the case of the Hitchin integrable system?
I never thought about it, and probably I don't know enough about Hitch integral systems. But does it came from some maximal degenerations or things like that?
Sorry, I didn't quite catch that, but the reason I'm asking is that Guyotto-Moore-Knightsky, in their study of the semi-flat degeneration of the Hitch integrable system, have some, at the time, what seemed to me a rather irritating change of coordinates that I think they called psi, which is exactly of this form where you have to change the angle coordinates with respect to the action variables. And it seems very likely that if it's something canonical, it matches what you're suggesting here. But I'm just curious if there's any kind of more canonical interpretation of your S1 in that context.
So something I need to know is that Hitch integrable system, I think, is something like a singular Lagrangian torus fibrations. And to have this kind of business, I need to have some kind of pencils so that this one came as a limit as a singular fiber, so that you can take this particular Hamiltonians, which is absolute value of this map. And I don't, as any kind of particular kind of, map which correspond to FQ. That I don't see so much in that example.
I see. Okay, thank you.
Maybe can I just ask a question using audio? Is it clear that there are really chaotic regions? I mean, you know, of course, KM says that generically there'll be some regions of chaos, but
I mean, yes, that's something I need to calculate. But you see that this particular Hamiltonian small f, this one, yeah, this functions f, and I need to see this. You take some generic level of this f. You have some 3 manifold, and this 3 manifold has 12 end, which is tori. There are some kind of integrable systems, but I will be surprised that the Hamiltonian of f is very much integrable on a generic level.
Wow. But it's not.
This looks very complicated.
Yeah.
And maybe somebody who is very good at the computer might try to draw the dynamics of this f. Then one can do it, but I don't know.
Okay.
This is very much a complicated function. So.
Okay. Thanks.
Let's see, you have a question from Simon Rezchikov. Simon, go ahead.
Oh yeah, my question was just, so, you know, KAM theory, I mean, I've sort of spent a little bit of time learning it, and there's this part of it which talks about how if you do a small perturbation of an integrable system, it still has an integrable part. But then there's another part of, I guess, what people in the KAM literature call KAM theory, which tries to describe what happens like at the boundary of the integral part and the non-integral part. So there's all these like very refined descriptions, like these, you know, the boundary torus breaks up into a Cantor set of tori and stuff like that. So I was curious if you thought about whether there could be any, you know, interpretations of that in terms of the sort of more algebraic or Floer theoretic perspective. I don't know very much about mirror symmetry of the Nabokov ring, having no real idea how to think about it. So I'm just sort of very curious because that's you know, that's a very traditional part of KAM theory, and it's a very interesting part.
Yeah, so I have some crazy possibility. That's the following things. So suppose you have this mirror symmetry. So you have this S0B and S1B, right? And we can consider this as a kind of object of a scheme over scheme or rigid space over this Novikov ring. Then you have some kind of, you know, this guy may be related as a kind of formal power series of lambda 0. And this guy seems to have some algebraic geometric meaning. And but you know, if this formal power series converges, then it is a bit contradictory because this picture shows that all tori just survives. That's not correct. So something I want to I can expect is that this guy is some kind of equivalent so this seems the middle of this is this line boundary P over this strange field, and this one is equivalent to some other thing, which might be some kind of a this is a kind of automorphism of this category of coherency. So it's a middle should be some Fourier-Mukai transform which converges, and the map from this guy to this guy is some kind of equivalence over formal power series. And in the traditional KAM pictures, it is known that in a sense of formal power series, kind of all KAM tori survives, but because of the small denominator that is destroyed. And the part when this divergence happened is something related to what you mentioned. So something kind of dream is that if you can understand this relation between this formal power series and something convergent in algebraic geometry, then the mirror symmetry may say something about which tori survives. But that's something. Maybe it's just crazy.
Are there any other questions for the speaker?
I had one question, which maybe I'll ask over voice. Thanks for your talk, by the way. I was just wondering whether there's anything to be said about higher iterates of this FQ map. I mean, I guess these estimates, depend on the fact that you're doing the time one return, but do the estimates get much worse very quickly?
So you consider this FQ, and you want to get these iterations. That's something like you take these pencils, right? And you can just compose, and you can study these pencils. So that's kind of way how to take this how to look this iterates in this kind of way. But I don't know what happens. For example, if we consider this domain which corresponds to this vertex, then this is I think is a kind of 3 periodic point. So you iterate 3 times, this gets constant tori, and it should again you have this kind of bifurcation phenomenon. But that doesn't see from this picture, so I don't know how to understand it. Maybe you need to see how this compositions and some blow up, that kind of things I don't know.
Okay, thanks.
Okay, well, if there are no further questions, maybe this is a natural breaking point. And for folks who want to stick around for the discussion section afterwards, you are welcome to do so. So let's give Kenji another hand.
Thank you.